Now we will start with our third project. So in our third project it is heat transfer. So I'm going to show you some basic heat transfer modeling today, and then definitely you will do it by yourself and you have your third assignment. So let's start with that. I got a very simple model, and I believe you know how to import the geometry or analysis. So you can draw your geometry by using any software, so it's up to you. So we got the geometry today, something like that. So look here, we have a wall. So this wall is in between two fluid domains. So this is the one fluid domain, this is another fluid domain. Let's say we're taking some small section of the total system. So you see here we have this fluid domain, we have this fluid domain, and in between these two fluid domain we have a solid wall. So now we want to see how heat transfer happen. So let's say this is the hot fluid and this is the cold fluid and this is the wall, and we actually do two different types of test. So the first is the parallel flow, and you know what is parallel flow. Parallel flow means the hot fluid and the cold fluid, it will go to the same directions, and when it is the counter flow, then the hot fluid and the cold fluid direction should be opposite. So let's start with the meshing. And for meshing, the most important thing is you need to do some name selections, because software doesn't know your problem, so you need to introduce what you are going to do. So you already know these four options. So let's start with the name selections. So I would say this is our working light. Okay, so this is working light, and let's say this is the cold light. So that means if it is working light and if it is cold light, so see working light and the cold light, so that means it will be parallel flow. So similarly this one, it will be the hot outlet, and this will be the cold outlet, right? So we have done with that, and now I'll select this wall. So see, I selected the whole body for this wall, so I'll put this name is wall. I'll say this is the hot fluid domain, and I'll say this is the cold fluid domain, right? So we have done with our this is a very simple model. So we have done with the name selection. Say cold fluid, hot fluid domain, wall, cold outlet, hot outlet, cold light, and hot light. So once I have done with this, I'll go to the mesh. So you see, definitely the solver is fluent. We're going to use fluent. If you use any other solver, then you can change it, but we'll keep with this fluent, and this is definitely CFD. So let's see how it goes. Like, I will click on generate mesh with all the basic setups. So you see, created some hex mesh in this model. This is very simple model with no complexity, the change of curvature and nothing. So you can use this hex mesh for this domain, and it will give you better quality. So now we'll refine the number of nodes. So you know how to do this sizing. So go to sizing, and we need to play with this different minimum maximum size. So you can see the max size is 1 into 10 to the power minus 3. So if I make it maybe 0.6, let's say 6, and here you see the minimum size is, the curvature minimum size is this. You see the diffuser size is this. So I just changed the max size, and if I click on generate mesh, let's say not that much change. So if I increase one more zero here, then it will show some error here. So what I will do is because you see this is 10 to the power 5, the max size, and the element size is lower than that. So I need to play with that. So let's say 0.00, maybe 7. Still it is showing some error because it should be lower than that. So let's say maybe 576, something like this. So now it's not showing any more error. And if I click on generate mesh, and if I wait a little bit, you can see it gives us most final mesh. So let's check the number from the statistics, how many nodes we have. It's a lot, like 0.5 million nodes. So what we can do is maybe we can reduce this number a little bit, because especially for the demonstration purpose, it is difficult to deal with that number of mesh because it will take a long time. So what I will do, maybe I will change this number, something like that, and I will click on this. So you see it gives us more coarse mesh. So still it's 150,000. So if I change a little bit more, let's say this is 9, and if I change, so let's say this is 99, and if I click on generate mesh, so it's more or less the same. So yeah, I think it's a good number. So we'll keep this mesh for our simulation and check the quality of the mesh. We can check the orthogonal quality here. So the orthogonal quality, the minimum orthogonal quality is on, because you see this is quite good mesh. Actually, this is very simple model, and we're using the hex mesh. So they're all, you see, actually from this figure you can see it's very good mesh. So the quality is good. However, maybe the mesh is not stable. So when you see the quality is minimum quality is on, that means this is excellent mesh. So don't think that it will be stable. It could be that this is a good mesh, but solution could be unstable. So definitely you need to do the grid refinement test. Anyways, I'll close this one. Let me delete this one, otherwise it will take time. So now click on update projects. So it will take a little bit time, Usually Workbench, when you click on update Workbench, try to update every component like setup, solution, results. So that's it's a bit slow. Yeah, you see it updated the setup, but we did nothing with the setup yet. Yeah, but it's working. It's trying to update the solution, results, and it will show some error. You see, it's showing here unable to update solutions because we did nothing with that. Anyways, we'll just ignore this error message. So now click on the setup. Oops. So click on the options, double precisions, and keep this setting as it is. So now we will get the fluent window. Okay, so it's updating the mesh. Click on OK. So we have the domain here. You see we have all about domain. We're going to calculate the heat transfer, so definitely we need to solve the energy equations that I discussed during the class, and in this video it's not possible to discuss everything, but I'm showing you the process. So check the energy equations, click on OK. We can use the K-epsilon model. So we're going to use the scalable all functions, understand that, and I will keep the other setup as it is. If you need to change anything for your future projects, you can do it from here. That's what I discussed during the class. We don't need the other thing here, so what I will do is now I will go to the materials. So the fluid materials is definitely it's not air, so we will keep this material is water. So go to the fluid database, scroll down, you see this is the water liquid. If you need to change any properties, you can change it from here. So copy it, close this one, close this one. So you can see we got the water liquid here, and the solid is the aluminum. If you have any other materials, you can change it from here. And yeah, you already know because this is your third project, so you have done 2 other projects, so you know how to change the material properties. The important thing is, you see we got air and the liquid, so go to the cell zone conditions. So this is our cold fluid domain. So you see the material for the cold fluid air, change this onto the water liquid, right, and click on OK. The same thing for the water fluid. So this is water, also water. So click here, select the water liquid, click on OK, and check the wall. So this is aluminum. So right, if you want to change the properties, you can do it from here, or you can do that from the material properties list. So I'll keep this on as it is. So we don't need this air anymore, so delete this and just right click and delete. Yes. So now you see we have the water liquid and the aluminum, right? So now just let me have a look. Okay, I can't close that one. So you see here we have done with the materials, the boundary. Now the boundary conditions. So the boundary condition is very important. So for the cold inlet, this geometry, this is very small dimensions. It's very small dimensions. So what I'm going to do is, maybe I will use very small velocity, let's say 0.05 meter per second for the light velocity for the cold fluid, and the temperature is, let's say it is 30 degrees centigrade, right? So click on OK. For the cold outlet, you see we are going to use the the gas pressure, so click on OK. For the hot inlet, so for hot inlet we're going to use the velocity is the same, like 0.05, and the thermal condition is, let's say this is 360. So just the random value I'm putting. So for the hot inlet, that's the same thing. And now the wall. You see this is the wall hot fluid domain. So for the hot fluid domain we're going to use, this is the stationary wall. So thermal condition is the constant heat flask, right? So we'll keep this on. For the cold fluid domain, the same thing, this is the constant heat flask. The important part is the wall, especially you see this wall in between 2 fluid domain. So we're going to use the system coupling, okay, biosystem coupling, and I'm not giving any wall thickness right now because I actually want to show you some different options. So use the biosystem coupling and click on OK. Okay, if you want to see actually the why this section, like actually if you confused you like what is wall 1, so what you can do, you can go to the boundary conditions, just double click on the boundary conditions, highlight the zone, and you can say this. So it will clearly show you actually this is your wall conditions. This is the the interface between these two wall. So what we did from the boundary conditions, we select the biosystem coupling because we want to see the heat transfer from the water and the cold fluid, right? So we have done with that. So now what we will do is we'll go to the solution methods. So I say we're going to use scaffolds for first, because I say I'm going to show you some other options, so we always use the second order. So select the second order. For the solution control, so you can see some of the relaxation factors, spatial momentums, the flow current number. So I explained that on earlier. So I'm just going to keep this number as it is. I'm not changing anything. Go to the monitors and click on the residual. So increase this value maybe into the 5. So yeah, and then click on OK. So for the initialization, I'm going to use the hybrid initializations. It's pretty quick. And now I'll run the simulation here. Actually, I'll run it for maybe 1000 iteration, let's see. So if I click on the calculate, so it will take a little bit time. Okay, so you see here, if you want to see the scalar residual, just click here. So you see the solution is converging. If you look at the continuity, the other, like the X, Y, Z energy and the turbulence model, they already converged, and that it's the all are 10 to the power 8, 9, 7, 5. So they already converged. But for the continuity, it's still in 2. So now it becomes 3. We need up to 5. So we need to run the simulation until it converges. So it's running. I believe it will converge soon. You can see it's going down. So if you see this residuals are going down, all of these curves are going down, then you should expect that okay, your solution will converge. And if you see it is straight, it's not changing, you can check the number here. If you see it's not changing, that means yeah, if you run for a long time, yeah, it will not converge. So now I think we need to wait a little bit more. So what we will do, we will stop this video here once the solution is converged, and then we will do some post-processing in other videos. Otherwise this only will be lengthy. So now see it is still 10 to the power 3. Yeah, so now it's 10 to the power 4. So definitely it will converge. The solution will converge because it's continuously decreasing. So you see it's very close to 10 to the power 5. Yeah, so it raised that values, and yeah, the solution will automatically stop very soon. I think I have selected the continuity is 10 to the power 5. Yeah, so it will automatically stop soon. So you can see here, yeah, so you can see the calculation is complete up to 300 iterations. So we're doing the steady calculation. So you see we're using the steady model. So once your solution is converged, solution will automatically stop. So we will stop this video here, and I will create one more video to show you the results, and I will play with some other options to give you some understanding actually how to deal with the the heat transfer problems.